Welcome back to part 3 of IP addressing for CCNA. What we're going to be talking about today is first a little bit about host addressing, and then we're going to have a look at how subnet works, how subnet masking works. So we haven't talked about host addressing yet. Remember that we've decided how the routers and PCs and so on work out, where the network and host portion, where they're split. We've seen how a router, for example, would put the network portion of the address into its routing table. What we want to have a look now is what happens to the host portion of the address. So let's just take this Class C address here. You can tell it's Class C because the first 2 bits are set to 1, the last third bit set to 0. That's Class C address, which means only the last 8 bits are host. So with that last 8 bits, we've got a possible range of from all zeros up to all ones. That gives us 256 combinations from 0 to 255 decimal. 256 combinations. However, we can't use the first one. The all zeros address represents the bit of wire itself. Remember the routing tables from part 2. The router put into its routing table an address like 10.0.0.0 with the host portion all set to zeros. So the all zeros address is the bit of wire. It's the network. The other one we're going to reserve is the top one. In other words, the all ones address. We're going to call that the broadcast address, and if we send anything to an address where the broadcast, the host portion is set to all ones, it means the packets go to every device on that particular network. So all ones in the host portion of the address means the broadcast address. That gives us an available range of addresses from 1 up to 254 with our Class C address. So we've pinched or taken away 2 of the addresses that are available, the all zeros address and the all ones address. Okay, so we understand the network portion of the address, we understand the host portion of the address. So we're a company, we get given a Class B address. We get given the address 172.16.0.0. Have a look at the first octet. It's a Class B address. So the first 16 bits are network, the last 16 bits are host. That means we've got 65,535 host addresses available to us. So what we're going to do is grab the biggest, longest piece of Ethernet wire you've ever seen in your life, and we're going to attach 65,000 hosts to it. And we're going to turn them all on, and it'll work, yeah? Wrong. Remember collisions. We've got one enormous collision domain now, and all those PCs and servers and whatever are all contending for the same piece of wire, the same bandwidth. And so that is just not going to work. We're going to have far too many collisions on there. We're not going to get any communication going whatsoever. What we need to do is split it up. So here's one way of splitting up that long piece of wire. What we could do is put a router between segments of Ethernet cable, and then we could attach a number of hosts to each segment. A number that we know won't cause too many problems with collisions. And one thing we know about routers is that they first of all split up collision domains. So any collisions that happen on the top link will not affect the second link down. We also know, we've got an extra advantage, that routers stop broadcasts from being propagated between segments. So we get 2 advantages from here. We get smaller collision domains and smaller broadcast domains. Any broadcast sent on the top segment will not affect any of the other segments. Okay, and then for administrative purposes, what we're going to do is we're going to number everything on the top segment. We're going to call that 172.16.1.0. So everything on the top segment will be 172.16.1. something. And then on the second segment, we're going to create 172.16.2, the third segment down, 172.16.3, fourth segment, 172.16.4, and so on. So we're going to split those up, and that's going to make it nice and easy for us to administer. If we've got a problem with 172.16.1. something, we know where the device is. It's on the top segment. So that's what we'll do then. We'll program a router up. Here's just the top 2 segments. On one side of the router, we have 172.16.1.1, and all the other devices attached to that segment are 172.16.1. something. And on the Ethernet 1 segment, we're going to put an address of 172.16.2.1, and all the devices on there will have an address of 172.16.2. something. And then we'll turn on the router and have a look in the routing table. And guess what we see? The router is looking at the most significant bits. And it's saying, okay, I get this. I've got a Class C address one side, 172.16.0.0 out of Ethernet 0. And I have a Class B address out of the other side as well, out of Ethernet 1, which is also 172.16.0.0. You see, the router has no way of determining that there are two different networks on each side. All it's looking at is that most significant bit and saying they're both Class B addresses and in fact the same Class B address. So what we need is a way of the router to be able to distinguish between the 172.16.1 part of the network and the 172.16.2 part of the network. What we'd like it to do is something like this. We'd like the routing table, when we look at it, to reflect the difference between the two Ethernet segments. We'd like one half of it, the Ethernet 0, to show up in the routing table as 172.16.1.0, and the other half to show up as 172.16.2.0. And there's the problem. We have to now tell the router that we want the first 3 octets to be considered as network on the Ethernet 0 side, and the same on Ethernet 1. And then it can distinguish between the two and put 2 different addresses into the routing table. So the question is, how are we going to do that? Enter subnet masking. And the rules to subnet masking are very simple. Wherever there's a 1 in the subnet mask, that means this is the network portion of the address. And wherever there's a 0 in the subnet mask, that means this is the host address. So we're going to put a mask after the address that says how much of the address should be considered network and how much of the address should be considered host. And we're going to use decimal numbers, because we don't understand binary, to represent those ones or noughts. So just take a look at this. We've got an address here, 172.16.2.17, and a mask that follows it, in our terms, is 255.255.0.0. As far as the computer is concerned, router in our case, it sees 8 bits in the first octet, 8 bits set in the second octet, 0s set in the third octet, and 0s set in the fourth octet. So it knows by looking at that mask that the first 16 bits should be network and the last 16 bits should be host. Okay, we're going to continue this on a little while later in part 4, so stick with us, keep on going. If you don't understand any of it, go back, rerun it, have another look.